Okay, so let's go on. In the next talk, I'm going to focus on the global signal and dynamic functional connectivity methods. And in particular, this will be about how the global signal impacts dynamic functional connectivity, such as sliding window functional connectivity, coactivation patterns, and the subsequent measures, states, occurrences, transitions you can derive from them. But then secondly, also, how some of these methodologies can be applied to actually analyze and perhaps better understand the global signal. And so, I don't think I need to introduce dynamic functional connectivity to this audience. It has been a hot topic for more than 10 years now, and there are many review papers out summarizing this. And I'm going to visit the most important methods with respect to what they can contribute to global signal and how global signal interacts with them. So first of all, the most straightforward method of dynamic functional connectivity is certainly sliding window functional connectivity. You simply take your favorite functional connectivity measure, typically Pearson correlation, you apply some temporal window in a sliding window fashion, and you get one functional connectivity value per window position and per connection, of course. And like that, you can, like it is shown here, you can look how this dynamic functional connectivity value varies over time. You can identify perhaps periods of hyperconnectivity and other ones of hypoconnectivity and study dynamics like that. And of course, there is one important parameter here. The key parameter is certainly the window size. The shorter you take it, the faster order dynamics you can access, but also the more you lower the signal-to-noise ratio, and actually the more you might introduce aliasing artifacts. But that's not really the topic of today, but I just like to mention it nevertheless. So if we look at this sliding window functional connectivity as a time-dependent functional connectome, you get these beautiful movies. These are three subjects for a session of resting state. And of course, there are many ways to analyze this. But one way of analyzing it I would like to show you, in particular because it's relevant to global signal, is the following one. So you have this time-dependent FC, and let's rearrange it in a data matrix where we now unfold all these functional connectivity values as the rows and all the time points, all the window positions as the columns. And then we can do this per session, per subject, and let's now center each connection so we take out the average dynamic functional connectivity value for each connection over each session, so that the data matrix only has the fluctuations of dynamic functional connectivity left into it. And if you apply a singular value decomposition, or if you like, you can see this as a PCA, what you get are the components that explain the fluctuations of this data matrix. And what you see, number one, that shows up at the top is a global fluctuation pattern. And so in this data, we are purely sensitive to the variations in sliding window functional connectivity. So it does drive a global connectivity pattern that has the most explained variance. Now, if on the original data you would have applied global signal regression, you actually do remove this first component. And the first one will be the second one here on the slide. And I think that's probably the reason that in most sliding window functional connectivity methods that go for states, so that apply a clustering instead of an SVD, they do global signal regression, because otherwise, obviously, this will become a major confound in your dynamic FC states. So let's move to the next method, which is based on the point process analysis concept, where you typically take a time course of a seed region, you normalize it, and you look with the threshold at some of the peak values to identify some key events. And then one first thing you can do, as Tom already alluded to, is you can average all these selected frames. And that is often referred to as a stationary cap, which is a proxy for a seed functional connectivity map. And the mathematical formula you see there, like the expectation of your data conditional to where your seed is exceeding a certain threshold t is indeed a proxy for a correlation value. And now, if you look at how, for instance, PCC stationary cap suffers from global signal regression or not, well, as already shown previously, you do see there is a major impact. And no surprise, I mean, you also have this in the seed functional connectivity map itself. However, the real power of coactivation patterns is that you would do temporal clustering. And so you don't have just a stationary cap, but you come up with a whole repertoire of caps, which are different spatial configurations whenever your seed is exceeding a certain activity level. And in this case, if you now compare with and without global signal regression, well, there is still, let's say, an increase in the coactivation level as you would expect, but it's not as striking as you have it on the stationary cap. And this already alludes that the interaction between the dynamics of some seed-based caps and the global signal might actually be more complicated than the stationary view would suggest. I'm coming back to that in a bit later too. Now, what is very nice with the coactivation patterns methodology is you can apply it not only to your seed time course, but you could also take the global signal itself to guide the CAPS approach. And so in that case, you can look at the global signal, apply a threshold to it, you select fMRI frames, and if you compute a stationary cap, which is the average of all these selected frames, you get the so-called global signal peak map, which is, again, a proxy for the global signal correlation map, for the same reason I just explained in the case you would take a seed regions time course. But of course, now you can also go to a temporal clustering approach, and now you end up again with a repertoire of caps, but this time driven by the selection of when the global signal is high. And this gives you a very nice, let's say, a rich characterization of different spatial configurations that do happen when the global signal is high. And in addition, these caps, the occurrences of these caps, are modulated by rest versus task. That's very nice. Still, how exactly this underlying, what exactly is the underlying mechanism that drives this is still complicated, because you can imagine, for instance, that the global signal is altered by the task because breathing or heart rate is altered. And at the same time, the task will, of course, also modulate the cognitive responses. And so that brings us, or let's say that brings me to the next slide, which has been based on work of many people, and I like to cite the recent review by Zhang and Northoff, because I think they summarize it well and they have an extensive list of references I like to refer to. But essentially, they come up with this interpretation that you can think about a global signal, well, firstly, as being according to a single layer model. So the global signal would reflect brain-body coupling, such as respiration, cardiac, and so on, in addition to some subcortical projections from the basal forebrain that is modulating all these physiological processes. And therefore, it reflects, for instance, arousal, as has been demonstrated extensively. But next to such a single layer interpretation, you could also move forward to a dual layer interpretation, which is actually suggested by the global signal caps that I just showed you before, where on top of this, now what you can see as a background layer, there is a foreground layer, which is showing us that the global signal unfolds into these different global signal caps. And so there is a dynamic repertoire of spatial configurations that's right on top of these global signal peaks, and that would suggest that global signal is indeed intricately linked to cognition as well. Maybe it's coordinating, maybe it's modulating, but it suggests a link. Now, as a final method of dynamic functional connectivity, I like to bring up an approach that we proposed a couple of years ago, which we refer to as total activation, and it's essentially a regularized hemodynamic deconvolution approach. So let me try to explain a little bit of the mathematics, because it's important to understand how it could give an insight into the global signal. So in this approach, the deconvolution, the hemodynamic deconvolution, is based on minimizing this variational criterion you see on the slide. So F is the measured signal, depends on space and time. F tilde is the recovered signal. And then you see there is like a round D, which is the derivative operator, and there is the inverse of a round H, which is the inverse of the hemodynamic system, which you could imagine to be modeled by a linear approximation. And so what this term is telling us is that you want to approximate the measured signal F by the signal F tilde in such a way that the fit of the signal, when you would apply the inverse of the hemodynamic operator to it, you get the so-called activity-inducing signal. And when you apply the derivative to that activity-inducing signal, the so-called innovation signal is sparse. Now, sparsity can be expressed in this variational criterion by the second term, which is called the regularization term, and which actually is a sum of absolute values, or mathematically an L1 norm, and that is known, if you optimize it, to pursue sparsity. So in other words, the bottom line is that this type of criterion will give you an approximation of your fMRI signal in such a way that the derivative of the inverse of the deconvolved signal is sparse, and that we call the innovation signal. And that means that the transients in your signal should be, in essence, sparse, so it should be localized in time in the end. Now, why do I tell all this? Because there is actually automatically, when you optimize such a criterion, a term that should be added, which is this F tilde naught, and which is so-called the a term out of the null space of the derivative of the inverse of the hemodynamic system. So that's a whole mouthful, but it's essentially the part of the signal that your operator is canceling. If you do a derivative, you cancel out the constant. So if you get back to the original signal, you need to add it back. That's the constant in that case is part of your null space. Now here we have a derivative and another leaky derivative, if you want, which is the inverse of the hemodynamic system. So in the null space contains smooth polynomials. And those you can think about as possibly global signal components or contributions. Okay, now, given all this explanation, let's look how the, well, if you do this approach, how this can, what this shows and what this can learn us about global signal. So first of all, with this approach, we can get to this innovation signal, which is showing us the transients in the fMRI. And then we can do caps, so temporal clustering, directly on the transients. And if you do this, you get, again, a set of innovation-driven coactivation patterns. Before showing you one example, there is one particular cap that often shows up, which is actually very interesting, I think, because it's showing a visual sensory network in positive combined with actually basal forebrain regions in negative. Okay, this is often shown in global signal studies. Tom also alluded to it, where there is this known anti-correlation of the global signal with these subcortical regions. Now, in this case, it's driven by transient activity, which should be compatible with the hemodynamic response by the very nature of the mathematical optimization. So that's one cap, but if you look at the whole set of caps, there is not something here like a constant map or something that is suggestive of a global signal topography as such. And that means, because of this optimization, that the global signal actually does not follow the response of a hemodynamic response function. And thus, if there is something more smooth, it ends up into the null space, and it doesn't corrupt, if you want, these innovation-driven coactivation patterns. Now, by that virtue, the background layer, if we think again about the dual layer model, this background layer contribution should be filtered out because it's not compatible with, let's say, transient hemodynamic responses. And the surface layer could still remain compatible with this finding because we have two possible interpretations here. First of all, the global signal can be seen as an increased synchronization between transients, and the global signal topography as a superposition of the networks represented by these different ICAPs. So those could still be explained by the ICAPs methodology. So to conclude, a few takeaway messages. When you think about global signal and dynamic functional connectivity, I think it's important to look a little bit into the specific measure you're working with, as well as, let's say, the aggregation technique, which could be clustering, which could be SVD, that you're applying to these measures. And depending on this choice, the global signal might be mixed into your measure, or the global signal could be separated out and clearly identifiable, or it could also be that your method is invariant to the global signal, like the last one that I showed you. And this can also help with interpreting your results if you, for instance, what is often done, you apply whatever you do in terms of dynamic functional connectivity, and you compare what you have with and without global signal regression. Secondly, neither the global signal time course nor the global signal topography is orthogonal to the time course or the spatial patterns of our functional networks. And so that means that if you have global signal regression, actually the order of your processing steps does matter, because regressing out global signal will take away part of the expression of the functional networks as well. Next one is that, as we have shown, we can apply dynamic functional connectivity methods to the global signal, like with the global signal-driven caps, and we have seen that these caps, global signal caps, are not stable over time, and nicely disassemble into a set of transient global signal caps. And finally, of course, the global signal turns out to be more intricate than expected. One way of thinking about it could be with the dual layer model, but essentially the brain and the body can probably not be completely separated, and everything we do will point towards this level of being intertwined. And last but not least, let me send a global thanks to my very dynamic team and you for the attention. Thank you very much.
We have one question for you, Dimitri. What is the evidence that key events are actually key events? And how do you estimate the likelihood that they are extreme outliers or noise that should be censored?
Sorry, can you repeat?
Right. So at some point, I think you talked about key events in your talk. And the question is like, what is the evidence that key events are actually key events and not some outliers or noise that should be censored?
Well, I mean, typically, before you get to selecting your key events based on the time course, you're going also to apply some cleaning approaches to your data. So if you have properly dealt with motion and other, let's say, respiratory and other types of possible artifactual contributions, you can assume that whenever your time course of a seed is exceeding a certain threshold, it is, let's say, driven by underlying activity.
Fantastic. Let's move on with Professor Lucina Udin. Thank you.